In chapter 18, we're going to look at the equilibrium between acid and base. Before we get started, let's take a look at these pictures. These atoms look familiar to you? Do you know that they contain acid and base? And if you do you know what type of acid and base they contain? Let's spend a minute to think about what kind of acid and base they contain. If you are not sure about your answer in the previous class, look at this table. This table shows us the molecular formula and the name for the acid that are contained in those products. For example, we have acetic acid in vinegar. For citric fruits, we have citric acid. And for vitamin C, it's actually ascorbic acid. In lab number 7, we're going to use titration method to quantify the concentration of vitamin C in a commercial vitamin C product. Right. For the base, you can see we have sodium hydroxide, which is used in cleaners, also ammonia and sodium phosphate. Right, so a lot of these bases are being used in cleaners. So in chapter 18.1, we're gonna look at the acids and the base when they dissolve in water. Let's quickly review the definition for acid and base. We talked about them when we go over chapter 4 last semester. Right, so compound to be named an acid means that when it dissolves in water, it will dissociate and generate this hydrogen plus ion, which is also called a proton. And for a base, when it dissolves in water, it dissociates and generates this OH anion called hydroxide. Again, proton and hydroxide ion. Right. So for the proton, when it exists in water, it actually combined with a water molecule, right? Because the lone pair electron on the oxygen in water, right, will attract this positively charged proton. So they actually form this H3O positive ion, which is called a hydronium ion. But by convention, we don't write proton in this form, right? We just use H plus to represent this hydronium ion. But you should know that actually when inside water, it is the hydronium ion, not by proton itself. All right. So in chapter 4, we also talk about the acid-base reaction, which is also called a neutralization. Right. So when you mix an acid and base, they will react and form water. Right. So for example, in this case, if you have an acid and a base, remember this is called the molecular equation, right? Just showing out the overall equation, right? But if you separate each ionic compound, each acid and base, into their corresponding ions, right? You can write the formula in this way, and that's called the total ionic equation. And because this X minus and the metal is the spectator ions, we can delete them. Right? So the net ionic equation is a proton plus hydroxide give you water. Right? So for all the acid-base reaction between strong acid and strong base, right? So we can say that the net ionic equation will always be proton plus hydroxide and give you water, right? But if it involves a weak acid or weak base, it's no longer the case, right? For this net ionic equation, the delta H is negative 55.9 kilojoule, right? So it's a isothermal process, meaning that for each mole of proton reacting with each mole of hydroxide and generating one more water, is going to release 55.9 kilojoule. Before we take a look at the interaction between the acid and the base, first let's look at the acids. Right, so the acid can be divided into strong acid and weak acid. And we already talked about this in chapter 4. Right, so for an acid to be strong, it means this acid will completely dissociate. Right, so in this example, we have this nitric acid. Right, so this is a strong acid, means when it dissolves in water, will completely dissociate. Right, so notice we use a one-sided arrow, right, to represent these reactions almost achieve completion, so we can ignore the equilibrium. Right, so for weak acid, it doesn't completely dissolve, right, only partially dissolve, depends on how weak it is. Right, so in this case, we have to consider equilibrium, so we use this double-sided arrow to represent this reversible reaction. Right, so strong acid and weak acid, they can react differently, very differently with the metal. Right, we know the metal can be corroded by the acid. Right, so if we add a piece of zinc in hydrochloric acid is a strong acid, so you can see this bubble, right, formed. There's a lot of bubbles involved. But if we put the zinc in a weak acid, right, in this case, this weak acid is acetic acid, you can see a very little amount of bubble is formed. In this table, we see this common strong acid and the common weak acids. Right, so you don't have to memorize which are strong, which are weak, and I will give you that information in the exam. Let's take a closer look at this dissociation of strong acid and weak acid. For a strong acid, because we said it almost achieved 100% dissociation, so the proton generated is almost equal to the initial concentration of the strong acid. To represent that, we can use this figure here. So before dissociation, this green bar demonstrates the concentration of the strong acid. But after dissociation, you can see the molecule, right, the molecule of this acid is almost gone, right? But instead, it generates this proton and the anion, right? So the concentration almost equal to the initial concentration of the acid. So for weak acid, right, because it only achieves partial dissociation, so at equilibrium, only a few of the acid is dissociated, right? So you can find this green bar only decrease a little bit, and that difference matches the magnitude of the acid, the proton and the anion generated. Right, so because the strong acid is fully dissociate, we use a one-sided arrow, but for weak acid, we use a double-sided arrow, right, to represent the equilibrium condition. So when we write the reaction quotient, right, using these concentration terms, for a strong acid, right, we have the product over the reactant. And notice here the water is actually in the liquid phase, right? So we know for liquid phase or solid phase, right, we replace it by a number of 1, right? So meaning that the activity is equal to 1, right? So we can actually ignore this concentration term of water here. So because it's almost 100% completion, the product, right, the concentration of product is way higher than the remaining concentration of the reactant. Right, so as you can see in this figure, right, so the QC value at equilibrium, which is Kc value, is way greater than 1. But on the opposite end, for weak acid, because at equilibrium the amount of the product is very small compared to the amount of the acid remained, so this QC value at equilibrium, right, which is Kc, is way less than 1. In the previous slides, we saw that for strong acid, which completely dissociate, right, for weak acid, it partially dissociate. To extend this level of dissociation, or the position of this equilibrium when the acid dissociate, we can use this term Ka to represent the extent of this dissociation. So here K is still the equilibrium constant, and A represents the acid, right? So it actually the equilibrium constant when when the acid is being dissociated. So in this example, we have an acid, and we can say that at equilibrium, the Kc is equal to the concentration terms of the products divided by the reactant. And again, because water is at liquid phase, so its activity is equal to 1, so we can delete that term. Right, so what's left is equal to Ka. Right, so Ka is equal to the concentration of proton multiplied the concentration of anion divided by the concentration of the acid molecule, and they all should be at equilibrium. So because this product on the top, right? So when we have a strong acid, that strong acid is gonna have a large Ka value, right? Because this fully dissociation generate more products, and for a weak acid, this Ka value is gonna be small. So to compare how strong the acid it is with another one, we can compare their Ka values, right? So we can measure their equilibrium constant, right? So if the higher the Ka value, the stronger the acid. This table gives you the Ka value for some common weak acids, right? So for strong acid, their Ka values are much higher than this, are greater than 1. But for weak acid, you can see their Ka values are much smaller than 1, right? From the 10 to the negative 2 to all the way to 10 to the negative 10. Right? So as you can see, when this Ka value increases, the strength of the acids also increases. So like the acid, the base also can be divided into strong base and a weak base. Right, so a strong base either have a OH group, right, in their formula, like a sodium hydroxide, it contains this OH, or it could be a metal oxide, right, so like a potassium oxide or sodium oxide, calcium oxide. So when this metal hydroxide dissolve in water, it will generate this metal cation and the hydroxide ion. Right, so when the metal oxide dissolve in water, it will also generate this metal ion and the hydroxide ion. Right, so for a strong base, right, it's either the metal oxide or metal hydroxide. So they will fully dissociate and generate this hydroxide ion. And for a weak base, right, so they do not contain the hydroxide ion in their formula, like ammonia, right? So you do not see OH, but they can generate hydroxide ion by ripping off a proton from water. So water is HOH, right? It has this bonded structure. So a weak base can actually take a proton, right, from the water, right? So what's left is this OH, right? So a weak base indirectly, right, generate this hydroxide ion, and you notice this double-sided arrow, right, meaning that it will not fully react, right? So it will only produce a little bit amount of hydroxide, and that's why we call it a weak base. Right, in this table, you can see a lot of common. They use a strong base, and ammonia is a weak base. In chapter 18.2, we can look at the auto-ionization of water and the pH scale. Right, so we're gonna introduce the term pH, although you have heard it many times previously, but we never look into detail about what is exactly pH and how is pH calculated. In previous chapters, we learned many special features of water. For acid and base, it is also very special, right, because for a water molecule, it contains both the proton and the hydroxide. Right, so if you just have pure water, these water molecules can actually reacting with each other. Right, so in this figure, you have two water molecules. Right, the lone pair electron on the oxygen in the first water molecule is gonna attract or rip the proton from the second molecule, right? So generating this hydronium ion and the hydroxide. Right, so this process is also known as auto-ionization or self-ionization. It's highlighted self or auto because we didn't add anything to water. Right? We just let the water molecules react by themselves. Right, so in this equation, we have two water molecules, give you a hydronium ion and a hydroxide. And we know hydronium ion is actually a proton combined with the water. Right, so we can actually shorten this reaction by saying that it's a one water molecule. Right, so it will dissociate, so generating this one proton and one hydroxide. So for the water at equilibrium, right, meaning that when the dissociation process is at equilibrium, we can write that Kc equal to the concentration of hydronium ion times the OH divided by the water concentration square. And because water is a pure liquid phase, so for pure water liquid phase, its activity equal to 1, so 1 square is also equal to 1. Right, so we can write this dissociation constant, right? So Kw, right? So that's for this dissociation constant for water. Right? For acid is Ka, right? So for water is Kw. So this Kw is equal to Kc times 1 square, right? Which is here. So that's going to be equal to the concentration of hydronium ion or proton, right? So you can, these are interchangeable, right? So then times the concentration of the hydroxide. And the value is very small, right? It's 10 to the negative 14, right? So meaning that although this self-ionization, right, can occur in water, but the extent is very small, right? So on the 10 to the negative 14 level. So for a cup of water, it not only contains water molecules, right, which is the majority molecule inside this water, it also contains this proton and the hydroxide. And because this proton and hydroxide are generated, right, from the dissociation of water, and their coefficient are both equal to 1, so their concentration is actually equal. So when you have water by itself, alright, when you have water by itself, the amount of hydronium ion or proton is equal to the amount of the hydroxide, right? So their concentration are equal, and because they're the product, right? When you multiply their concentration, they're equal to 10 to the negative 14. So for each of them, their concentration are equal to 1 times 10 to the negative 7, and this is at room temperature. So if you add, right, acid or base into water, that's gonna change the amount of proton or hydroxide, right? If you add acid, that's gonna increase the amount of the proton. If you add base, that's gonna increase the amount of the hydroxide, right? So a change in the concentration of proton will also cause a change of the hydroxide, and that change is an inverse change. If you increase the proton concentration, that will decrease the concentration of hydroxide. Similarly, if you increase the concentration of hydroxide, it's gonna lower the concentration of the proton. Right. So for acid, when we say this is an acid solution or acidic solution, right? So that means the proton concentration is higher than the hydroxide concentration. Right. For a base, dissolved in water, which give you a basic solution, right? The amount of proton is less than the amount of the hydroxide. And for a neutral solution, we said their amount are equal. This figure here summarizes what we just learned in the previous 2 slides. Right, so if you want to calculate the concentration of hydronium ion or the proton, right? So people normally write the hydronium ion as this proton, right? So they are the same thing. So using this water dissociation constant, so at room temperature, right, is equal to 1 times 10 to the negative 14. Right, so if you know the concentration of hydroxide, you can calculate the concentration of proton, or the other way. And again, right, so to tell whether a solution is acidic, basic, or neutral, we just compare the concentration between this proton and the hydroxide. For a pure water itself, right, without adding anything, the water is a neutral solution, right, because the amount of proton and the hydroxide generated are equal to each other. Right, so in that case, at neutral condition, their concentration are equal to 10 to the negative 7. Right, it's the same and for both of them. Right, so you can see for acidic solution, the concentration of proton is gonna be greater than 10 to the negative 7, and for the hydroxide, it's gonna be less than 10 to the negative 7. Right, so for a basic solution, the concentration of a proton is gonna be less than 10 to the negative 7, and the concentration of hydroxide is gonna be greater than 10 to the negative 7. So let's work on this example problem, right, to calculate the concentration of proton and the hydroxide. Right, so this chemist adds some of this hydrochlorine gas into pure water at 25 Celsius and get a solution, right? So because we know HCl is a acidic compound, right? So we know it's gonna generate acidic solution. But let's use our calculation, right, to determine what type of a solution it is. Right, so in the question, it tells us the concentration of this hydronium ion or the proton is equal to 3 times 10 to the negative 4. Right, so we want to calculate the concentration of hydroxide. If you have a piece of paper available, right, so pause the video and calculate the concentration of hydroxide. Right, so using the formula, right, we can say the hydroxide concentration is equal to the Kw divided by the concentration of the hydronium ion or the proton. Right, so because at room temperature 25 Celsius, this is the Kw divided by the concentration of a proton, so this is the concentration of a hydroxide. And because the proton concentration, right, is greater than this hydroxide concentration, so we say this solution is acidic. Another way to express the concentration of this proton is using the term pH. So you can remember this term by thinking of it as a power of a proton, right? So the power of proton, pH. So the pH equal to the negative log of the proton concentration. Right, so remember there's a negative sign in front of the log. Right, so for example, if you have a solution, right, contains 10 to the negative 12 molar of a proton, right, the pH is gonna be equal to the negative log of 10 to the 12. Right, so the log of 10 to the negative 12 is equal to negative 12. And because you have a negative sign in the front, right, so that's negative 1 times negative 12, which is equal to positive 12. Right, so the pH is equal to 12. Right, so if you know the pH and you want to calculate the concentration of a proton, the proton concentration is going to be equal to 10 to the negative pH. Right, for example, if your pH of the solution is equal to 5, right, so if the pH is equal to 5, that means the proton concentration is gonna be equal to 10 to the negative 5. Right, so if you have a pH of solution equal to 1, that means the proton concentration is gonna be equal to 10 to the negative 1. Right, so it's gonna be equal to 10 to the negative 1 or 0.1. So you can see the lower the pH, right? The lower the pH, the higher the concentration of proton or the hydronium ion. And that's because of this negative sign, right? That's because of this negative sign in front of this log term. Right, so when we say, okay, we want to change the pH, we want to increase the pH, right? Increase the pH, that means lower the concentration of the hydroxide, the hydrogen ion, right? So a basic solution, right? That means you have a low concentration of a proton, high concentration of hydroxide, right? So that means it has a high pH, right? For acidic solution, it has high concentration of proton and a low pH. So let me write that down. So for acid, right, for acidic solution, right, the pH is less than 7. Right, pH is less than 7 because the proton concentration it is greater than the hydroxide concentration. Right, so for a base, right, we say the pH is equal to greater than 7. Right, it's actually greater than 7. So the hydroxide concentration is greater than the proton concentration. Right, so why 7? Remember, when at equilibrium, the proton concentration is equal to 10 to the negative 7, which is equal to the hydroxide concentration, right, which is also 10 to the negative 7. Right, so based on the definition of pH, right, so that's pH is equal to 7. So when the concentration of a proton is equal to 10 to the negative 7. Right, so when the concentration of a proton increase, right, so the pH will be less than 7, right? So this exponent is gonna become higher. So we have a higher proton concentration than the hydroxide concentration. Right, so for a base, the pH is greater than 7. That means the proton concentration become much smaller than the concentration of the hydroxide. Right, so this slide just summarizes what we learned in the previous 2 slides. Right, so again, for a pH less than 7, we call it acidic solution. Right, so for a basic solution, the pH is greater than 7. A neutral solution, the pH is equal to 7. And on this chart on the right, you can see this pH range of some common acid and base. Right, so the stronger at the acid, the lower the pH value. Right, so for our stomach acid, which is in the pH range of 1 to 3, right, so that means the concentration range of this acid is in between 10 to the negative 3 to 10 to the negative 1. Right, so that we know that's mainly hydrochloric acid. Right, for pure hydrochloric acid, right, the pH is equal to 0. Right, so for a 1 molar concentration hydrochloric acid, the pH is equal to 0. And for 1 mole sodium hydroxide, the pH is equal to 14. Right, so meaning that it mainly contains the hydroxide, and the concentration of a proton in this case is equal to 10 to the negative 14. Right. For 1 molar sodium hydroxide, the proton concentration is very small and equal to 10 to the negative 14. So like pH, we can also have a term POH, right? So that's the power of hydroxide. So that's a native log of a hydroxide concentration, right? So same idea. So if you have a basic solution, right, this POH gonna be less than 7, right, if you have a basic solution. Right, it is gonna be greater than 7 it is an acidic solution. Right, so pH and pOH, they're opposite, right? So, but their total, right? So their total is actually equal to 14, right? 14 is the native log of the water dissociation constant, right? So because we know at room temperature, this Kw is equal to 10 to the negative 14, right? By taking the native log of it, it's gonna be equal to 14, right? So and this 14 is the sum of a pH and the pOH of a solution, right? So from this operation process, right? So you can see when you take a native log of something, right? That this native log is like represented by this lowercase p, right? So pH is the native log of proton, right? So pOH is the native log of a hydroxide, right? So that's the P and the OH, right? So this P is actually taking the native log of something, right? So if you have a Kw, there's a pKw is going to be the native log of a Kw, right? So from this relationship, it's going to be very easy for us to determine the pH or pOH if we know one of them. If we know the pH equal to 5, that means the pOH is going to be equal to 14 minus 5, which is 9. Right? So if we know the pOH is 11, that means the pH is going to be 14 minus 11, which is 3. Now let's look at this practice problem. If you have a paper, pause the video for a few minutes and try to solve this by yourself, and then play the video again to learn about the answer. Right, so in this problem, we try to calculate either the hydroxide, the hydronium ion, the pH, and also the pOH. Right, so with the given information. So it's at room temperature, so we know the Kw, right, is equal to 10 to the negative 14. That also means that the sum of the pH and the pOH is going to be equal to 14. Right, so for solution A, right, because it is a strong acid, right, nitric acid is a strong acid, so it will completely dissociate, so the concentration of the proton is going to be equal to the concentration of the starting acid, right? Because for strong acid, it completely dissociates, so we use this one direction arrow, so the concentration of proton is going to be also equal to the concentration of the acid. So the pH is the native log of this concentration, that equal to 0.52. Right. So for the pOH, right? So instead of calculating the concentration of hydroxide as it says here, and then figure out the pOH, we can just use like 14, right, minus 0.52. Right, that will also equal to 13.48, right, which is the pOH value. Right, for the hydroxide concentration, right, it's going to be equal to Kw divided by the concentration of the proton. Right, so we know at room temperature Kw is equal to this divided by the concentration of the proton. Right, so that's the hydroxide concentration. If you take the negative log of this concentration, right, as it does here, you can get the pOH value, right, which is the same as the way we minus the pH from 14. Right, so this is a much easier approach. Right, once we know the pH, we can calculate pOH. For B, we have a base. Right, so for this base, because each mole of this base contains 2 hydroxide, right, so you have to be very careful about this. Right, for this acid is a monoprotic acid. Right, so 1 mole of acid molecule give you 1 mole proton. But for this base, because of this subscript 2, right, that means for each mole of this base, it's gonna give you 2 mole of this hydroxide. Right, so if the concentration of the base is this, we need to multiply that number by 2 to get the concentration of the hydroxide. Right, so once we get the concentration of the hydroxide, we can calculate the POH, right? So the native log of this concentration. Right, so the POH is 2.08. Right, so again, we can calculate pH right away by subtracting 14, right, minus 2.08. Right, so that will give us this pH value. Right, so if we know the hydroxide concentration here, we can also calculate the proton concentration, which is equal to Kw divided by the hydroxide concentration. Right, so after you get the proton concentration, you can also take the native log of it and get the pH. Right, so that will be the same result here. There will be 3 homework problems. Right, so practice on how to calculate the proton concentration and the pH and understand their relationship. And I will post more videos regarding chapter 18 and chapter 19. Right, so as I mentioned in email, there will be 4 videos coming up for the next 2 weeks. Right, so because the class are canceled next week, so that kind of means that you don't have to study during next week, but I will post the video next week. So it's your choice to either study them next week or the week after, right? But you have to finish watching all these videos before the 3rd midterm, right? So I highly recommend to watch at least 1 video, maybe every 2 or 3 days, right? Just like you are going to classes Monday, Wednesday, and Friday. And for the videos coming up, I'm gonna post some problems in the video, and I will see how many of you can respond to those problems, right? So please be very active, right? So leave your comment or write down your answer in the comment, or if you have questions, you can email me also. Right, so there'll be more videos coming up next week, and have a good weekend.